Marseille, France, a thriving city today enjoying its Mediterranean climate. But not so far away is a cave that can only be reached by a submarine passage. It's just behind me over there. You can see the monitoring station with the pipe running down below. That goes into the cave to monitor the air conditions in there. That cave was only discovered a few years ago by divers, and it's very interesting because it was occupied 18,000 years ago when the sea level here was much lower, by people who adorned its walls with spectacular cave paintings depicting kinds of animals that they saw around them at the time, rather like the paintings at Lascaux, showing most notably, for example, reindeer. So the climatic conditions they experienced were obviously a lot different from those which we have today. Now let's go back, much further back in time, over 100 million years ago, to the early Cretaceous, when these massive limestones behind me were being deposited. Conditions then, too, were very different from those of today.
Climate change can vary from the familiar annual seasonal variation to quite pronounced mean global temperature changes if we change the timescale to hundreds of years. Bruegel's paintings, for example, vividly depict the icy grip of the Little Ice Age on northern Europe in the 16th century, while around 1,000 years ago, conditions became warm enough to allow Norse seafarers to establish thriving settlements in Greenland. Timescales in thousands of years bring in the Pleistocene glaciations. Orographic perturbations of climate, like that caused by the uplift of Tibet, operate on a timescale of millions of years. And over even longer time spans, of tens to hundreds of millions of years, the Earth has fluctuated between extremes of warm greenhouse climate and cold icehouse conditions. This programme compares the Cretaceous greenhouse world with that of the icehouse world today. In the Cretaceous, polar ice was much reduced and limited to mountainous regions, with little ice reaching sea level. In lowlands quite near to the poles, there were forests, where now there's only snow, ice or tundra. High sea levels flooded the continents to produce broad shelf seas. These ones shown here flank the Great Tethys Ocean, which then separated the southern and northern continents. Here are the present-day continents placed in the positions they would have been in during mid-Cretaceous times. And this is where Marseille was. So let's ignore the present-day Mediterranean Sea and concentrate on the cliffs to get an idea of the Tethyan limestone sediments, what they contain, the conditions in which they were deposited, and what they tell us about the climate in the Cretaceous. The fossils present provide the clues we need. With Peter Skelton, a paleontologist at the Open University, is a research colleague from the University of Provence at Marseille, Jean-Pierre Masse.
Ici, nous avons cette couche à rudistes.
They're looking at the cross-sections of some tubular shells from one of the most abundant fossil groups called rudist bivalves in some early Cretaceous limestones. Rudists are extinct today, but flourished in the Cretaceous, spreading throughout shallow marine areas in low latitudes. This cluster comes from a seamount in the Pacific. Examples such as these would have lived like present-day fan mussels, anchored within the sediment and growing vertically.
This is a really beautiful bed of these bizarre rudist bivalves. Jean-Pierre, is this a typical assemblage of rudists for this kind of sequence?
Yes, it's typical. It's diagnostic of some parts of the Cretaceous in the northwestern part of the Mediterranean, especially in Portugal, in Spain, and also in Sardinia.
Oh, that's fantastic. So that really shows how enormously expanded these communities of very shallow water, shelly organisms were.
Yes, this kind of low diversity assemblage is really well known in that part of the Mediterranean area.
Not far away, another fossiliferous outcrop added greatly to the environmental picture.
We have here these calcified sponges in life position, like that, and another one parallel to bedding, suggesting some physical disturbance in this association.
I see, yes. Well, I think perhaps we can see the same kind of thing here as well. These rudest bivalves have been preserved in life position here, but up here we have them all higgledy-piggledy. They've been rolled around, so presumably this suggests periodic current activity. How would you interpret the kind of environment in which these rocks were deposited?
I think this suggests very shallow water deposition in probably high energy environment. It means with some tempest tide, some storm effects in this organization.
More evidence for the rough weather conditions can be seen in other tempestite deposits further up the cliff.
Oh, Jean-Pierre, come and look at this. We've got a very nice, strong contrast here between these coarse layers made up of broken shelly material here, for example, and up here. And by contrast, this very fine material here with fine laminations running through it.
This could be related to a beach system.
Oh, it could actually be as shallow as a beach, then, give this contrast.
Yeah.
Scattered throughout the succession were these curious dome-shaped objects. Elsewhere in the area was a rather better example of this fossil structure.
Oh, this is nice, Jean-Pierre. We've got a couple of coral specimens here. I think our students will be quite intrigued to know why they show this sort of concentric banding here.
It's a cross-section through a domal coral with gross rhythms here. And this kind of structure is typical of corals living now in tropical seas with symbiotic algae.
Oh, I see. So, of course, these would need to photosynthesize. So this presumably shows us that they would have been living in relatively well-lit water, quite shallow, well-lit water.
Yeah.
Other shelly fossils found in close proximity were this fine example of a calcareous sponge, a sea urchin, thick-shelled gastropods, and other forms of colonial coral, as well as these burrows of some soft-bodied organism, possibly a marine worm. All these fossils imply deposition of loose shell sand and debris in shallow water conditions, building up expansive platforms of limestone beds. But how much carbonate was involved in the deposition of such platforms?
Jean-Pierre, this is the section we were looking at yesterday. I understand it doesn't represent the whole of the Lower Cretaceous, but represents a particular part of the Lower Cretaceous, running from about sea level there up through that splendid thick bed of limestone with the cross bedding in, right up to the top of the cliff up there. You've measured this section in some detail. What sort of thickness do we have there?
It's about 400 meters, and it represents about 5 million years.
That's 400 meters in 5 million years.
Yeah.
Well, putting those figures together, that'll give us something like 80 meters of limestone deposited on average per million years.
Of course, the vertical rate of accumulation varied from place to place and at different times, but the figure of 80 meters per million years will do as an average for such Cretaceous Tethyan platforms. But to calculate the volume, we need the area. This map shows Tethys as it was somewhat later in the Cretaceous, when the shelf seas were even more expanded, around 93 million years ago. If we take the area that was covered by platform limestones at this time, some 9.5 million square kilometres, according to estimates by a team of French geologists, we get approximately 750,000 cubic kilometres of limestone deposited per million years. This corresponds to 0.25 kilograms to the power 12 of carbon buried per year in these Tethyan platform limestones alone, more than the total rate of carbon burial in all limestones today, including oceanic as well as shallow water deposits. But for the Cretaceous, we also have to add limestones formed outside the Tethyan area and in slightly deeper water, such as this stuff. The White Cliffs of Dover are made of it, chalk, which extended as thick blankets across large parts of northern Europe, southern Russia, and the American Midwest. These chalks probably buried as much carbon again as the Tethyan carbonate platforms during late Cretaceous times. But we don't stop there. There's more carbon to consider yet. Going back to Tethys, here's a map of the platforms from earlier in the Cretaceous, which shows the basins lying between them. One of these basins lay to the north of the Marseille platform limestones. In this deeper water area, known as the Vacantian Trough, we find yet another major sink for carbon.
Hugh, you've been looking at some of these basinal sediments in the Vacantian Trough. Tell us a bit about what they're like.
Yes, well, a characteristic of those sediments in the Vacantian Trough is that they're black. They're black because they contain high contents of organic carbon. This indeed is a feature of many rocks of mid to late Cretaceous age.
What do they look like closer up?
We might just look quickly at this example here. It actually comes from Tunisia, so we've jumped across the Mediterranean with one bound. But you can see in detail it's very finely laminated on a millimetre scale. So that's telling us that the sediments have been undisturbed once they've formed on the seafloor. They've not been churned and mixed and bioturbated by seafloor dwelling animals. So the implication there is that the bottom water conditions were inhospitable, almost certainly anoxic, and it's in those anoxic environments that the organic matter has accumulated.
And was this phenomenon restricted to the Tethyan area? Or?
Certainly not. We could look at this example here. This actually comes from the northeast of England. It's actually a detail from the English chalk. And once again, you can see that it's black, it's laminated, and it's, again, organic carbon rich. So this phenomenon is certainly Europe-wide.
Okay, but in this case, it sort of forms a sandwich between two layers of fairly normal pale chalk. So what does this tell us?
That's exactly right. When you look in closer detail at these Cretaceous sequences, even those that look rather monotonous and homogeneous, like those in the Vacantian Trough, you find, in fact, there are certain levels which are particularly rich in organic carbon. And it's usually the same levels, i.e. levels of the same age, that you tend to find again and again as you move round the globe. So there were these certain intervals when particularly organic carbon-rich sediments were deposited. We could even hop into the Atlantic Ocean. This is a core, taken quite a long time ago now, off North America. And you can see there's a very clear distinction between black laminated sediments and white sediments, which show some lamination, but again are much more obviously bioturbated. So this again is telling us that the sea floor was extremely inhospitable and anoxic during this interval of Cretaceous time.
What do you suppose could have given rise to such widespread anoxia, even in the oceans as well as shallow shelf seas?
I think to answer that question, one really needs to take a global view. We've just illustrated examples from Europe and the adjacent ocean, namely the Atlantic. But we can actually hop to the Pacific. This is an example of a Cretaceous black shale. Again, it's laminated, and again, the interval of time during which this was deposited reflects the same intervals that one can pick up in Europe on the evidence of these organic carbon-rich beds. So we seem to be looking at a global phenomenon, so any explanation we should advance needs to take that into account. I think most people would now suggest that probably we're dealing with an increased flux of organic carbon to the sea floor, probably dependent on an increase in planktonic productivity, in turn probably dependent on an increased flux of nutrients into the photic zone where it can be utilised by the plankton. At the end of the day, I think the point to stress is that huge amounts of carbon were being buried in the ocean, some in shallow seas, as you've shown, but equally an awful lot as organic carbon in deep sea sites. And somewhere, therefore, we have to search for the source of this additional carbon.
Together, the burial of organic and carbonate carbon had an immensely important economic spin-off: oil. Many petroleum reservoirs were created when porous rudous limestone formed next to organic-rich source rocks in adjacent basins. The limestones became soaked in oil, the black stains here. It looks as though the surface of the Cretaceous world was like a giant mop soaking up carbon dioxide. So the Cretaceous geological record poses two outstanding questions. Where was all the extra carbon dioxide coming from? And why was the sea level so high? Both were important factors contributing to the greenhouse world of the Cretaceous. One theory compares seafloor spreading rates. In the Cretaceous, seafloor spreading was more rapid than today. As the warm, expanded young ocean floor was pushed sideways, it therefore created broader mid-ocean ridges than those of today, which displaced more water from the ocean basins. So sea levels rose, generating the great marine incursions into the continental areas. That might go some way to explaining the higher sea levels and the more equable temperature variations, but was it the only influence? And where did all the extra carbon dioxide come from? The answers to these questions take us to the Pacific and the search in the 1970s for ancient ocean floor.
So there you were, drilling the Pacific Ocean floor. What did you hope to find when you first went there?
Okay, well, let's just start by looking at the East Pacific Rise, which runs up here. Clearly, that's the youngest crust. And to find the oldest crust, obviously enough, we decided to go right over to the western part of the Pacific, where the magnetic anomalies told us that it should be of Jurassic age, probably late Jurassic age.
And did you find any Jurassic ocean floor there?
No, we didn't find any Jurassic ocean floor at all. That was the major surprise of the leg. And we had a 2-month scientific cruise out there, and after the end of that, we were still in Cretaceous. But it was Cretaceous basalt and Cretaceous dolerite, intrusive and extrusive rocks with little rafts of sediment tucked in between that.
How does that differ from what you would have expected to find if you had been drilling original ocean floor?
If it had been original ocean floor, we would have expected to find Jurassic basalt with Jurassic deep-sea sediment on top. So what we were finding was evidence for a huge extrusive and intrusive event in this part of the Western Pacific. The evidence for all this excessive, intrusive and extrusive volcanic activity was not just concentrated in the area that we drilled here, but was widespread across much of the Cretaceous Pacific.
If I go across over on the eastern side, I don't see the same kind of sunken volcanoes that we have over here on the west. What was happening over on the eastern side?
Okay, well, if you look at Western South America, you can see there's a subduction zone along here, so all the Cretaceous seafloor has gone. Oh. Now, if you were to go further north into Central America and Western North America, particularly around California, you could find blocks of basalt, many of which are capped by shallow water limestone, and these have apparently come off edifices like these that we find over here and have been incorporated into the edge of the continent. So the implication of that is, I think, yes, the ancient part of the Pacific Ocean, this all but vanished plate, was like the Pacific plate during the Cretaceous.
Now, obviously, these things were presumably coming up to sea level. And do you have any evidence for that?
In some cases, yes. There seems to have been a broad thermal uplift of much of the sea floor, and then there are the volcanic edifices on top of that, and they certainly, in many places, did come right up to sea level with very, very shallow water limestones forming on top.
Some of the edifices are indeed capped by limestones containing shallow water rudis fossils. There are 2 further lines of evidence to suggest how widespread this form of volcanism was. By measuring the strontium isotopes in the shells of Cretaceous marine fossils, we get this graph of the strontium isotope ratio in seawater throughout the Cretaceous. Weathering continental rocks gives a fairly high ratio of strontium 87 to 86. By contrast, a much lower ratio comes with the hydrothermal flow from hot springs along mid-ocean ridges, oceanic volcanoes and the like. And so the value recorded in the fossils at any one time is a function of the continental and oceanic influences on the strontium ratio. Note that in the middle part of the Cretaceous, the values decline, And the favoured explanation is that it's related to an increase in hydrothermal activity and presumably volcanic activity in the oceans. A second and curious line of evidence comes again from certain rudist fossils. This late Cretaceous rudist species, with distinctive infoldings of its shell wall, has been found in the Caribbean area and in Arabia, with the implication that one of the populations must have migrated. They're completely unknown in the Mediterranean area, so they didn't use that migration route. The planktonic larvae of these rudists must have island-hopped their way across the Pacific. But how?
The ancient Pacific must have been studded with these edifices, essentially stretching from east to west.
That must have displaced a colossal amount of seawater from the ocean basins onto the continents.
I think that's right. We tried to do a calculation on how much water you would displace if a large tract of the Pacific plate was uplifted, and I think we came up with a figure something between 30 and 40 metres, just from the extant part of the Pacific. Now, if you believe that large tracts of similarly uplifted seafloor were there, but have now vanished, then clearly that figure would be greater. There's evidence that this type of excessive volcanism was not confined to the Pacific alone, but may also have characterised part of the Atlantic and Indian Oceans as well. So we're looking at a global phenomenon.
So, I mean, we could be talking here about another 100 or so metres of eustatic rise as a consequence of this.
That's certainly possible.
Okay. And so the implication here is that all this material was coming up, was being pumped through older ocean floor. Do you see anything remotely like that going on today?
Yes, if you look at the Hawaiian Emperor Seamount chain, which you can see here, this is the trace of a hot spot, a thermal anomaly within the mantle, over which the Pacific plate has slid. And you can see where the plate changed direction, where you get the point in the elbow, if you like. But this is responding very obviously to a point source. So what was different about the Cretaceous was that you have to envisage this sort of phenomenon operating, but on a huge scale. So we'd be dealing, if you like, with a super plume or something like that.
So we've got this huge area of volcanism coming up through the Pacific and other ocean plates. Can this help to answer some of the questions that we've raised about the Cretaceous greenhouse world?
Well, associated with all this volcanism, almost certainly was uplift of the Pacific plate. That would have caused a rise in sea level. The other possibility, of course, is that associated with all that volcanism, all those volcanoes, would be a huge increase in the amount of carbon dioxide in the atmosphere. So two very important effects, which would make the Cretaceous world very, very different to the one we know today.